So what is a continuous function? Well, your intuition may give you the following picture of what a continuous function should look like. It has to look like one nice continuous piece. On the other hand, if you have a graph of the following function, then it is broken here, therefore it should not be continuous. Well, you certainly have the right intuition. However, it is by no means easy to define what a continuous function is. Mathematicians actually debated on this for many years. But here is the formal definition. A function f is continuous at a point a if the limit of fx as x approaches to a is equal to fa. Let's take a look at a graph. Here is a graph of a function that you probably would agree it is continuous. Yes, it is continuous. Let's check the condition here. As x approaches to a, fx, as you can see, the limit of fx should be equal to this value. And that is exactly the same as fa. So this definition is satisfied for this graph. Now, this definition really means three different conditions. That is, first, fa must be defined. Second, the limit of fx as x approaches to a must exist. Third, these two have to agree to each other. In other words, the limit has to be equal to fa. If any one of the three conditions is failed, then f is not continuous at a. Let's take a look at some pictures here. At x equals to 1, as you can see, f1 is undefined because there's an open circle here. So limit does exist, but because f1 is undefined, fx is automatically not continuous at x equals to 1. At x equals to 3, the left limit and the right limit do not match. Therefore, the limit does not exist. So f is not continuous at x equals to 3. And then at x equals to 5, the limit does exist, but f5 is defined right here, and these two do not match. Therefore, fx is not continuous at 5 either. Okay, so those are the three ways a function could fail to be continuous. Now, we say f is continuous at an interval if it is continuous everywhere within the interval. Here are some basic properties for continuous functions. I won't go through the proofs, but they are pretty natural to have. First, the constant function is continuous. The function fx equals x is continuous as well. Second, if you have two functions f and g that are continuous, you can add them or subtract them, or you can take a constant times fx, or you can take the product f and g. You can also take the quotient f over g, and here the domain of f over g is where g is non-zero, of course. You can also compose them to get a composition function. And then all these functions are still continuous as long as we stay within their domain. So for example, if g should not be equal to 0. Okay, so from 1 and 2, we can imply a lot of simple functions that are continuous. For example, x squared minus 4 is continuous because, first of all, x is continuous from here. And then x times x, f times g here. So f and g are both x. F times g here is x times x, which is x squared. So that is continuous. And then 4 is continuous because it's a constant function. And then take the difference, and because we know f minus g is continuous, therefore this is continuous. More generally, if you have a polynomial, the same idea implies they are continuous everywhere. If you have exponential functions such as 2 to the x power, then it is continuous. You can also have a rational function. Remember, rational function is basically you're taking the quotient of two polynomials. So they are continuous as long as they are we stay within the domain. So for example, if you have this rational function, it will be continuous provided if x is not equal to 0. Same for square root or nth root functions, trigonometric functions, logarithmic functions. For example, if you have a square root function of x minus 2, then this is continuous provided if we stay within the domain, which is x is bigger than or equal to 2. Let's look at an example. Determine where each of the following functions are discontinuous. We have 4 different functions. Let's look at them one by one. First, question A. We have a rational function, therefore, by the theorem we just learned, it is continuous everywhere except when the denominator is 0. Therefore, continuous everywhere except when x is equal to 2. Let me show you the graph of this function. It's right here. You can see there's a hole here because when x equals to 2, it is undefined. I'm going to explain more why the graph looks like a straight line in a moment. Let's move to question B first. Question B looks really similar to A, same expression here when x is not equal to 2, but when x equals to 2, it is defined to be equal to 1. Okay? Well, first by A, this part is continuous everywhere except when x equals to 2. So now we have to determine what happens when x equals to 2. We need to determine the limit as x goes to 2 and see whether it matches with the f2, which is 1. Okay, the limit can be computed by factorizing top and bottom is already factorized. Okay, because first of all, when x goes to 2, we have a 0 over 0 type. So you have to factorize that to cancel out the 0. All right. The top is a quadratic function, and that can be factorized into x minus 2 times x plus 1. And now x minus 2 cancel each other. So you simply have x plus 1 left. And now you can substitute x equals to 2 and you get a 3. Now the question is 3 equal to f2? Well, f2 equals 1, so they are not equal. Therefore, the function is not continuous. And here is the graph. You can see why the graph, by the way, so this is not continuous, except it's not continuous at 2, but continuous everywhere else. Let me explain a little bit the graph here, because fx, we actually prove that fx is equal to x plus 1, provided if x is not equal to 2. So the graph looks like x plus 1, which is a straight line here. X plus 1 is a straight line because it's a linear function. When x equals to 0, y equals 1, so it passes through 0, 1, and the slope is 1, so it should look like this. Okay. Now, f2 is defined to be 3, defined to be 1 here, right here. So f2 is here, equals 1. So the graph looks like a straight line, except that there's a hole here, and then f2 is defined to be 1. This also shows why the graph for question A is like this, because this is really the same function except when x equals to 2. When x equals 2 is undefined, so you simply have a hole here. For question C, we have fx equals 1 over x squared when x is not 0. Otherwise, when x equals 0 is 1. Well, 1 over x squared is a rational function. It is continuous everywhere except when x equals 0. Therefore, we need to understand what happens when x approaches to 0. Let's calculate the limit. When x approaches to 0, basically we're looking at 1 over x squared, Well, x is very small when x goes to 0, so is x squared. So we have 1 over something that is really, really small. Therefore, the quotient becomes really, really big. So the limit becomes infinity. And that infinity cannot be equal to f0, because f0 is defined to be 1. So this function is not continuous, and here is the graph for that. It is not continuous at 0, but continuous everywhere else. For question D, we have the greatest integer function. Basically, this is the greatest integer that is no bigger than x. So for example, if x is 2.1, then the greatest integer of 2.1 should be just equal to 2, because it's the greatest integer that is no more than 2.1. Basically, this function will be continuous everywhere except when x is an integer. Let me show you the graph that explains that. The graph looks like the follows. So like for example, when x is between 0 and 1, well, like x equals 0.5, the greatest integer should be 0. So anywhere when x is between 0 and 1, it should be just 0. And then when x equals 1, suddenly jumps to 1. So, and then stays as 1 until when x equals to 2. When x equals 2, then f2 is equal to 2. And then stays there until x equals to 3 and so on. So that's the graph. And you can see that there's like a discontinuity at those integer points. Okay. Now these examples show 3 types of discontinuity. First, there is the removable discontinuity. Those are the ones that look like questions A and B. So the limit does exist, but the limit does not match with FA. Either that or FA is undefined. So they are kind of mild discontinuity. One can remove the discontinuity by redefining FA to be equal to the limit. Like in this case here, you simply need to define f2 to be equal to 3. Then it becomes continuous. Okay, so those are called removable discontinuity. And then infinity discontinuity. Those are the ones for which the limit becomes infinitive. It might be positive infinitive or negative infinitive, or might be positive infinitive from one side and negative infinitive from the other side. These are called infinity discontinuity. And then there's a jump discontinuity. Basically, the left limit and the right limit don't match, so there's a jump at this point. All right. So those are 3 different types, but there are some other weird types that we won't go through. Here is the most important theorem for continuous functions, the intermediate value theorem. Basically, the theorem says if a function is continuous on a closed interval AB, then if you pick any number between FA and FB, there is always a number C within the interval such that FC is equal to the given number. Let's take a look at a picture to see what the theorem says. Here we have the graph of a continuous function. X ranges from A to B. When x is equal to A, FA is here. When x is equal to B, FB is right here. Now you pick any number capital N between FA and FB. As you can see, we do have a number C such that FC is equal to capital N. In fact, you can obtain C as follows. You start with a horizontal line through capital N. In other words, the line y equals to n. It will cross the graph of fx at some point, and that is what C should be. Sometimes this horizontal line may crosses the graph multiple times. Like if n is here, then it will go across 3 times. In that case, you're going to just have 3 different C's that satisfies the conclusion. might be useful to think about this intuitively. So think about this line y equals n as a river. So basically, you start from one side of the river, you want to move to the other side. Let's assume the river does not have any bridge. And let's also assume you stay within this region, from A to B. In other words, you don't do crazy things like you go west into the Pacific Ocean and swim in the ocean and then come back to the other side of the river, okay? So let's assume that doesn't happen. Let's also assume that you don't take an airplane or take a rocket and then land on the other side. So you basically walk on the land. The theorem basically says that, if you walk continuously on the land, you will have to go across the river at some point, either by swimming or taking a boat or something. Unless you are truly a Superman, someone who can really jump, like you have a situation here, so you walk from here to here to here, and then you jump, suddenly you're going to the other side. And so of course, that is a situation where the function is no longer continuous. So this shows my first remark that the condition f being continuous is necessary here. My second remark is the condition fa is not equal to fb is a minor condition. If fa is equal to fb, you can still find a c by simply letting c to be equal to a or c equals to b. So in that case, c will be in the closed interval ab. So if you simply change this interval to closed interval, then you can drop this condition. My third remark, this is a very practically useful remark. The case when capital N is 0 is the most useful case. Let me make the statement here. In that case, the statement becomes, if fx is continuous on the interval ab, and fa is positive, fb is negative, or vice versa, in other words, fa is negative, fb is positive. So given that, then the theorem says fc is equal to 0 for some c. In other words, f must have a root somewhere within the interval. The intermediate value theorem is very useful in proving such a existence of such a root. Let's take a look at an example here. Okay, so here we want to show this equation has a solution within the interval from 0 to 2. Notice it is not easy to solve this equation explicitly because it's difficult to deal with cosine x. But we can actually prove, there is some solution, between 0 and 2. So to do that, we're going to apply intermediate value theorem. In fact, we're going to apply to this remark C here. First, we want to define the function fx. To do that, we move cosine x to the left. In other words, we define fx to be 3x squared minus 2x minus cosine x. We just have to show f has a 0 within this interval. Okay, so we're going to check the conditions. First, f is continuous. Yes, it is continuous because we have a polynomial minus cosine. Both polynomial and cosine x are continuous functions. Next, we compute f0 and then compute f2. f0 is equal to 0 minus cosine 0, but cosine 0 is equal to 1. So we have minus 1, which is negative. f2 is equal to, so substitute 2 here, you get 12, and then minus 4, and then cosine 2. That is equal to 8 minus cosine 2. Although we don't know exactly what cosine 2 is, but we know this is at most equal to 1. So this whole thing is bigger than or equal to 8 minus 1, which is 7, which is positive. So we have proof that f0 is negative, f2 is positive. Therefore, by intermediate value theorem, there has to be a c such that fc equals to 0. In other words, this is equal to 0. And that is the same as to say 3c squared minus 2c is equal to cosine c.